This hardware represents the absolute baseline of C++ memory allocation. Regardless of the syntax you write, every variable, array, and object ultimately maps to a flat, linear sequence of physical addresses. This diagram shows how a one-dimensional array physically occupies that hardware. It is a strictly contiguous allocation. 3 integers, 10, 20, and 30, are locked into back-to-back memory slots, each with its own sequential hexadecimal address. When dealing with two-dimensional arrays, the standard visual model shifts to a matrix of rows and columns, creating the appearance of a physical grid. But the matrix is entirely a human abstraction. In physical RAM, that grid collapses flat. A two-dimensional array is stored in one single continuous row, laid out sequentially row by row in memory. Visualizing this linear truth is required to understand C++. You cannot manipulate memory addresses directly with pointers until you discard the spatial illusions of the syntax. A string in C++ operates on this exact same linear principle. It is simply an array of characters with a strict mechanical boundary. Looking at this diagram, the word mnemon ends with a null terminator. This ASCII 0 acts as a physical wall, signaling to the compiler exactly where the allocated memory stops, so it doesn't read adjacent garbage data. This linear structure forces a mathematical constraint. Why do arrays begin at index 0 instead of 1? This diagram shows that the name of the array itself is not a standalone object. It is a constant pointer. It locks permanently to the exact memory address of the first element. When the compiler reads array syntax, it translates it into pointer arithmetic. The index is not a position, it is a measurement of distance. The variable I dictates how many steps to move away from that base address. To access the very first element, the distance moved must be 0. Adding 0 to the base address leaves the pointer stationary, allowing it to read the first block. That is why the index must start at 0. Because this is pure arithmetic, the order of addition is irrelevant. Writing 1 bracket AR compiles exactly the same as AR bracket 1, because mathematically, 1 plus the base address is identical to the base address plus 1. The bracket syntax is a convenient mask. Underneath, arrays execute raw pointer arithmetic. While a normal variable like I stores a primitive value like 3, a pointer stores a physical memory location. Here, j stores the address of I, and k stores the address of j. To navigate this chain, C++ uses two inverse operators. The ampersand extracts the address of a variable, and the asterisk dereferences it, following the address backward to retrieve the original value. When you command a pointer to move, the language calculates the jump distance automatically. This split view demonstrates pointer scaling. Adding 1 to a character pointer moves it exactly 1 byte forward, but adding 1 to a float pointer leaps 4 bytes forward, because a float takes up 4 bytes of memory. Pointers are inherently aware of the data type they target. This scaling ensures operations land perfectly on the next variable, avoiding misaligned reads. When navigating memory, combining operators requires strict precedence rules. Pointer evaluation operates right to left. This graphic breaks down the syntax. Scanning right to left, *PTR++ moves the pointer's address first, dereferencing the original value. With pluses on the left, it moves immediately, reading the new value. Asterisk in the middle means the pointer stays stationary. The target value itself increments. That ability to modify the target value is what allows pointers to mutate data across isolated function scopes. By default, passing a variable into a function creates an isolated copy on the stack. Any changes made inside that function are applied to the copy, leaving the original data untouched. But when you pass the memory address instead, you create a direct pipeline. The function can reach across scopes and overwrite the original memory block. This pipeline creates a critical risk. Returning a local variable's address makes that pointer instantly invalid. The stack memory is wiped, leaving a dangling pointer aimed at garbage data. Pointers grant the capacity to engineer and mutate shared architectural space, overriding the default behavior of passively copying isolated values. We can scale these precise memory mechanics up to object-oriented systems, where classes bundle multiple variables into complex, contiguous blocks. This diagram illustrates how inheritance maps to physical hardware. A derived class object physically encompasses the base class object within its own memory boundary. A structural problem occurs when we attach a generic base pointer to this larger derived object. By default, C++ prioritizes speed through a process called early binding, making execution decisions during compilation. Because the compiler checks the pointer's type rather than the object it points to, the signal hits the outer base boundary and executes the generic base logic. It ignores the derived code completely. Without a way to bypass the pointer's static type, object-oriented systems remain rigidly locked in place, completely preventing any dynamic scalability. The C++ language solves this with the virtual keyword, an explicit override switch for the compiler. When we mark a base function as virtual, it activates late binding. The system now follows the pointer at runtime, bypasses the base boundary, and executes the specific logic of the derived object. You can now load a single array with identical base pointers and have each one trigger completely different functions, depending on the specific derived object it targets. The ultimate restriction on this architecture is the pure virtual function, designated by assigning the function to 0. This blueprint illustrates the effect. A pure virtual function has no body. It strips the base class of implementation, converting it into an abstract class. Because it lacks implementation, an abstract class cannot be instantiated. It exists exclusively as a rigid contract, forcing every derived class to guarantee its own custom logic. The exact same pointer mechanics that calculate offsets in a simple character array scale perfectly to orchestrate complex, dynamic, object-oriented architecture.